Okay, welcome to video number 4 in the Unit 12 unit on solutions. We're going to pick up here with Roman numeral 3, the solution process. You can see your objectives right there. I'm not going to read them to you. Let's begin. We're talking today about factors which influence how well substances dissolve in other substances. It's called factors affecting solubility, or factors affecting solvation. So when you talk about things which affect the speed that a solute will dissolve in a solvent, a lot of those things are very common sense. You come in contact with them all the time. I tell my students all the time, if you keep in mind two things that you drink, one of them is tea and the other one is soda or Coke, then you know pretty much everything you need to know about solubility. But we'll get there when we get there. Several things affect the rate that something will dissolve. First of all, the size of the solute particles. If I want to sweeten up a drink and I have the choice of either dropping in a sugar cube or dropping in powdered sugar, which one do you think would dissolve faster and cause my drink to become sweeter faster? If you said the crushed sugar or the powdered sugar, you're absolutely right. Because as I crush that solute into smaller and smaller pieces, it increases its surface area, which then allows more solvent, like water or tea or whatever, to get in there and pull those particles apart faster. I can also increase how quickly something dissolves, if it's a solid and a liquid, by stirring the liquid, by agitating it. And again, think about tea. If I sweeten up my tea, I pour in sugar, it'll just sort of sit there and dissolve very slowly. If I take a spoon and stir it, then it will dissolve faster, because what I'm doing is I'm increasing the motion of those particles, and they're running into the solute more often with greater energy, and they're taking it apart faster. I can also increase the motion of my solvent particles by increasing the temperature of my solvent. Because remember, when you heat something up, it causes the particles to move faster. Temperature is directly related to particle motion. And so heating something up, increasing its temperature, causes those solvent particles to hit the solute faster and more often, which in turn will take it apart faster. Now this is different whether you're talking about dissolving a solid or dissolving a gas. And we'll talk about this here in just a moment. Increasing the temperature generally tends to increase the solubility for solids. There are a few exceptions. Unfortunately, it's very hard to predict an all-encompassing rule for each and every solid, because every solid substance is different as far as how much will dissolve in a certain amount of water at a certain temperature. Fortunately, we have these really interesting things called solubility charts. You're going to see one on the next page. Oh, I've been hit. Okay, I'm back. Now we've got a solubility chart coming up right here. It shows you, well, actually several substances. And what you're looking at right here is a solubility chart. Down here on this axis, they have plotted temperature, and temperature increases from left to right. And they also have plotted how many grams of solute can be dissolved per 100 grams of water. Okay? And you see, for most of these lines, they curve up and to the right, which means that as temperature increases, most of these substances increase their solubility. Now some have very steep curves, which means you turn the temperature up just a little bit and they're going to dissolve much, much better. Some have very, very shallow curves, like this sodium chloride line right here, which means that its solubility isn't going to change very much at all depending on the temperature of the water. You also see some of these are curving down to the right instead of up. All of these substances curving down to the right, well, most of them anyway, are gases. And you'll find in just a minute that increasing the temperature of a solvent, if you've got a gas dissolved in it, will actually decrease its solubility. And like I said, we'll get to that here in just a moment. Pressure is another factor that can affect the solubility of a solute in a solvent. That's if you're talking about a gas dissolved in a liquid. It has no effect on solids in liquids or liquids in liquids. It's only on gases. When you have a gas contacting a liquid, there will be gas particles that will diffuse, that will dissolve into that liquid, but they will also dissolve out of that liquid oftentimes at the same rate. There will be an equilibrium. And so if you want to dissolve more of a gas in a liquid, you've got to change the pressure. You've got to increase the pressure. When you increase the pressure, then it's going to cause more molecules of gas to run into the surface of that liquid, and the more they run into it, the more will dissolve and the more will stay dissolved. This is referred to, that change causing a new equilibrium is referred to as Le Chatelier's principle. I'm pretty sure I pronounced him wrong. I'm sorry, I don't speak French. But anyway, he stated that if you have a system like gas dissolving into a liquid, it will be at an equilibrium of speed dissolving out versus speed dissolving in. If you do something and you change that system, if you apply a stress to it, then it will reach a new equilibrium eventually. If I take a soda and I open it up and take a drink, when I first open it, I'm changing the pressure over the soda so it fizzes and bubbles quite a bit, lets a lot of that gas out as that pressure is decreased. As I leave it out for a while, it will reach a new equilibrium. It will diffuse out at a certain rate and diffuse in at a certain rate. I put the cap back on it, then I've changed it again, and it will reach another new equilibrium until such time as it changes again. If I shake the bottle, if I open the bottle, take another drink, any of those things can change the rate that that gas is dissolving into and out of that liquid. I have something here called Henry's Law. And basically, Henry's Law says that if you increase the pressure over a liquid, you increase that gas's solubility. If you decrease the pressure over that liquid, then you decrease that gas's solubility. Again, think about soda. If you open a can of soda, if you open the bottle on a soda, you're decreasing the pressure, and so that decreases how much gas can stay dissolved, and the gas bubbles up out. For gas solubility, changing the temperature also, it's the opposite of what you would find dissolving a solid in a liquid. If you increase the temperature, it decreases how much gas can stay dissolved. Again, think about Coke, think about soda. If I have a hot or a room temperature bottle of Coke and I have one that's been in the refrigerator and I open them both, you're going to find that the one that's been warmer will bubble and fizz much more, because those particles are moving so fast that it's causing more of that gas to dissolve out, to remove itself from the liquid. Whereas if it's colder and those particles are moving slower, then it's not applying as much pressure to the gas that's dissolved, so it stays dissolved. So like I just said, if you increase the temperature on a gas dissolved in a liquid, more gas escapes. If you decrease the temperature, then more gas will stay dissolved. So the solid in the liquid and the gas in the liquid follow pretty much opposite patterns. Okay? Again, think about tea, think about Coke, and if you keep that in mind, in tea I'm dissolving sugar, in Coke I'm dissolving carbon dioxide gas and dissolving bubbles, then you can remember the rules for solid and gas solubility in liquids. Okay? Again, a couple examples. Soda. Interesting thing, you need to look up nitrogen narcosis, the bends, also called caisson disease, diver's disease. Very dangerous thing, and if you've ever done any diving, then you should know all about this, and if not, it makes for some very interesting reading. Just one more example of how the world around you is trying to kill you in interesting ways. So I encourage you to look that up sometime. Solvation is simply the process of dissolving. There's that SOL word root that I told you about in a previous video. Still means the same thing. Whenever you put a solute into a solvent, first thing that happens is that solvent particles surround those solute particles, and then secondly, those solute particles get pulled apart through random natural motion of the solute. Okay? They attach to it, they surround it, they pull it apart. When you talk about solubility, then you get into words like saturated and unsaturated and supersaturated. If I've got a substance, I dissolve a little bit of solute in it, but more can still be dissolved. That's said to be unsaturated, and I can add solute to that and keep stirring, and it will reach a point where no more solute will dissolve. And we say at that point that it's reached saturation, and no more will dissolve in there at that temperature. Fun fact, the opposite of something being dissolved is something being crystallized. So, if I say that I dissolved sugar in my tea, and then later the tea evaporated off, that sugar will crystallize, which is basically like saying it's undissolving. And so a solution reaches equilibrium where the solute is dissolving at the same rate that it's crystallizing back out. This would look like if you had a solid dissolved in a liquid, you would be able to see some solid particles down toward the bottom of the liquid, and they are constantly being dissolved by that liquid. At the same time, they're constantly being recrystallized. In your textbook, if you have one of our chemistry textbooks, there's some interesting values for solubility for different substances on page 404. If you don't have this particular book, then I'm sure you can Google it or do a Wikipedia search for solubility values. I'm sure there's probably an app for that. But what they will do is they will show you how much solute will stay dissolved in a certain quantity of water at different temperatures. It's going to be similar to that solubility curve you saw just a minute ago. And if I have liquids dissolving other liquids, then it's a little bit different set of rules. With liquids, you have to look at things like the nature of the solute and solvent, specifically are they polar or nonpolar. If they're polar, then they tend to dissolve other polar liquids. They tend to be what's called miscible. If one is polar and one is nonpolar, though, say for instance oil and water, then we say that they're immiscible, meaning that they can't be mixed. Okay, so there's a couple new words for you. If you can mix them together, they are miscible. It almost looks like it says mixable. If they cannot be dissolved in each other, they say that they are immiscible. And that brings us to the end of this video. Thanks for watching.